So this is the first example in the memory. In the memory, we have two different ones, immediate and register with the shift. So by looking at this number negative 26, we have to use this format. Just like what we did, we're going to go through this sequence. Opcode for memory, 0, 1. Now the BL is going to be 0, 0. It's on the table, but you can look at as a B, as is a byte? No, therefore it's a 0. Is a load? No, so it's a 0 as well. So you can look at that way. If it's a byte, STRB, okay, LDRB, then the B is going to be 1. And load is going to be 1, but all STR is going to be 0. That's why we have a 0 and 0. We good? And then I bar, obviously, it's going to be 0. Okay? I is 1, therefore I bar is 0. That's what we have. And then PW, for the PW, we need to know post or pre or offset. Offset is just for bracket, right, with those two numbers. Since we have a bracket with only register, that is the post index, so the P value and W value should be 0 and 0. Up to this point, you just need to follow these guys, B, L, I bar, P and W by looking at these bracket. And then because of this I, we know we have to use immediate. We good? This one is immediate 12, right? Do you remember data processing instructions? Immediate, how many bits of immediate? 8. We just had a quiz, pop quiz, right? It was just 8. And in the memory, we have a 12. And the branch, we're going to have a 24. So those are the three different types of immediate. We saw in the data processing, unsigned number for the 8-bit, and memory also unsigned. Take a note on that. Data processing immediate 8 is unsigned number. In the memory, immediate 12 is also unsigned number. Now we have negative 26. If you have a negative, we are not trying to convert this into negative number. We're going to put 26 as the immediate 12. How you take care of the negative? That's for U. So in U bit, if it's a subtract, it's 0. If it's 1, then it's an add. Since we need to subtract, we have to use U as a 0. And immediate 12 is going to be positive 26. Make sense? Immediate 12 is unsigned number. Now COND is going to be 1110. RD is 11. RN is a 5. And that is positive 26. Yeah. So for our class, we'll see either this guy or this guy. For this one, offset P and W 1, 0. For this guy is the post 0, 0. B and L, that's something looking at the byte or no and the load or no. So now when we convert to hex, it's going to be E405B01A. We have a LDR, R3, R4, and R5. This one is the register, right? Because we have now 3 registers, so we have to go with the second format. In the previous one, we don't have RM, it's all immediate. Now we have the third register. In order to find the memory address, now we need to add content of R4 plus content of R5. That's the memory address. Opcode is 0, 1 again. BNL is not byte, but it is load. So it's going to be 0, 1. I bar should be 1. P and W, we have a 1, 0. And U is the 1. And then COND is 1, 1, 1, 0. RD 3. RN 4. RM is 5 with the 1. And the rest is all 0. And that's hexa representation of the instruction. Okay, now STR R9, R1, R3, LSL number 2. So this time we have LSL that'll give us SH, and then shift amount shamped is going to be 2. So let's go through this. Up 0, 1. B, no. L, no. So it's 0, 0. I, no. So it's 1. P and W is 10, okay, is offset, and U is 1. COND 1110. RD 9, RN 1, RM and SH. Logically shift left is 0, 0, so this guy is going to be 0, 0. Shift amount is going to be 2, RM is 3, and here's the hexadecimal representation. Okay, what do we do in this instruction? What is it? Store. Let's say R9 as a given as a 0x ABCD. R3 is given 0x 10. R1 is also given 0x C. R3 is a 0x 10 in the binary number 00010000. That's a 10. In decimal number, it's going to be 16. 1, 2, 4, 8, 16. Now we need to logically shift left by 2 bits, then that's going to be the case. And when you change this into decimal number, it's a 64. Going from here to here, what happened? Multiply by 4. Why? How? Exactly, right? If you look at your instruction set, do we have a MUL, multiplication? Look for it. Do we have a multiplication in the data processing? There's no MUL, right? So basically there is no multiplication instruction. Well, in actually ARM, they do. Probably you will learn from your embedded. But in the MUL, in the ARM, you have to multiply register times register and then the result into the register. In your embedded system, ARM architecture, you have a 64-bit memory. So it's possible to multiply 32 times 32, we end up getting 64. However, for us, if you multiply 32-bit times 32-bit, there's no way we can store, right? 64-bit. Well, there is a way. So typical multiplication in our class, we have to use this guy. If we have 0, 0, 0, 1, what is it in decimal? 1. If I shift left by 1, if I shift one more, that makes sense because we are increasing by 1 bit, meaning when I move 1 to this guy, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So each shift to the left is equivalent to multiply by 2. So now shift left by 2, we need to multiply by 4. So now we want to add R1 plus after we shift left by 2 in the contents of R3, we end up getting 76. So now we find the memory address as a 76. What we do is a before, but after we execute this instruction, we're going to put R9 into 76. So the 76 as a memory address, content is going to change 0000ABCD. Next, branch instruction. We have B and BL. BL is branch and link. You can take a look at it from the textbook. We are not going to use BL for our class. The opcode is going to be 10, and then immediate 24 is that. This L bit is 1 for BL. So if you are using branch B high, B EQ, BLE, B whatever the 2 letter, this L value is going to be 0. And again, this immediate 24 is a sign extended. You need to make a note on that. Immediate 24 is a sign extended. So branch target address, BTA, we need to find that as a PC plus 8. Now we're going to convert this BLTL1 into 32-bit binary numbers. In here, we said PC. What is PC? It's program counter. Whenever we are executing series of these instructions, we fit in the process. In the single cycle, we're going to execute it one at a time. But typical our machines is a pipelined machines. So we just feed in all of these instructions, actually 5 instructions at a time. We can execute it because there are 5 stages of the pipelining in ARM architecture. So whenever we are executing any given instruction, PC, program counter, is going to point at that instruction. So right now, PC value is right here. Condition code 1011 because BLT, you can check BLT back there. It's 10, what is that right? BLT, right? 1011, and opcode is 10, B is 1, and L is 0. Now we need to calculate immediate 24. Here's the PC, right?
Right.
Okay. Now we need to look at the PC plus 8. That's the address as increment by what? 4. Why 4? 4 bytes per instruction is a byte addressing. 4 byte as a big endian. So the first byte, name of the first byte is A0. That's why we're using this whole instruction address as A0. Therefore, this guy is going to be what? PC plus what? 4. And then this guy is going to be PC plus 8. When we executing this line, we know the PC value. We're going to store that in that stage. And then at the same time, we can simply calculate PC plus 8. Once we know PC plus 8, now we need to calculate where we are going to branch. L1 is down there, right? So from PC plus 8, how many lines below is the L1? How many lines? 3. That's the immediate value for 3. Very bottom, I put the hexadecimal number as well. This opcode is always 10 for branch, and this one is always 1. And this one is if the BL, branch and link, is 1, all other branches is going to be 0. So next example, condition 0001 for this one. We're trying to find BNE. So BNE is 0001. Opcode is 10. This is 1 for all the time for branch and 0 for regular branch. Now we need to calculate this immediate 24. We have right now PC is pointing at here. PC plus 8 is here. Where we want to go? Go up by 1, 2, 3, 4, 5, 6. This time going up by 6. So we have to use negative 6 going up. So it's a positive 6 is 0, 0, 0, 0, 0, 1, 1, 0. And then negative 6 is a 2's complement, 1, 1, 1, 1, 1, 0, 1, 0. And for whole 24-bit, that's just a sign extension. That's why we have that. So that's the sign number as an immediate 24. In this problem, I want you to find the machine language binary number for this instruction. Okay? So basically, we are executing this instruction. So it has to be PC values right here. We are executing this so that you can convert this one into this. It really doesn't matter. When I execute here, our PC is here. So you can pretend you're executing here and you convert this into binary number. Are we good? And then when you're executing this guy, the PC is here and you can convert this as binary number. And so on and so on. Once you get to this, this is our PC value. The PC is there, but in these instructions, really doesn't matter the PC value. Why this is important? Because when we take this branch, we need to know exactly where to go. So when we're executing this, we know PC is here because meaning executing this instruction is PC value is right there, this guy. That's the good question. The PC value is actually this one, 0x8050. So actual happening is you have to use this value to add, subtract, to calculate the location of L2. L2 is 8040. So briefly, we're going to talk about this when we do the pipelining. But behind this logic, well, we have to use this address of BLEL2 is 0x8050. That's not going to change it. Right? It's a fixed value. So using this value to calculate where is L2. Yeah, did I do something wrong? Oh, good. There should be 1A. So hexadecimal value at the bottom, 1A, FFFFFA. Exactly. Downward is a positive, upward is a negative. Okay, so now some more conditional data processing instruction plus EQMILT. Then we need to obviously change the condition code, and then we're gonna execute this guy, the result of CMP. CMP with the 2 register, compare those, and if they're true, then we do subtract. If it's true, we do OR. If that is true, we do AND. So these are the condition mnemonics that you see from the handout. Here's the condition values, add EQ. Obviously, we're gonna put condition as a 0, and HS, where is HS? Right here, 0010, which is 2, okay? 0010. So I just list all of those here. And then the rest is going to be the same thing, just like what we practiced. From now, we're going to do some examples going backward. I gave you hexadecimal number. Now you need to change that into binary numbers and then find out which instruction actually representing by that machine language. So we're going to start with the op. That's what we did. So in the backward, the opcode is the first thing we want to check so that we know this is data processing, memory, or branch. And then IBIT, and we go from after that by example. So now we have E0475001. So if you put binary number, it's going to be this. Now, we need to look for opcode first, right? Opcode is 5th and 6th from the most significant bit, and it is a 00. Therefore, it is a data processing instruction. So it's going to be one of these three. Then next thing we want to look at is IBIT. Since IBIT is 0, so the top one is not our choice, and either this guy or this guy. Then what's next? Briefly talked about this guy, right? Pin number 4, pin number 0, 1, 2, 3, pin number 4. Pin number 4 is 0, this format. Pin number 4 is 1, this format. That is 0. Therefore, we're going to have the first one. So now CMD is 0010. That is a subtract. Therefore, we'll just highlight RN, RD, and RM and put it up. That's it. So I'm going to go through real quick which format, how we pick that. Opcode is 00. That's the first thing you want to find out. So either 00, data processing, 01, memory, 10, branch. Okay, those are the three types. Once you identify the opcode, and this is 00, therefore it's a data processing. Now we have these three choices. The first one is the immediate 8. Therefore, next thing you want to check is the IBIT, this IBIT. So next one IBIT, it is a 0, so it's not immediate. That'll give us these two. Now, major difference between these two, we have a fixed value of 0 right here, fixed value of 1 in here. So looking at the bit number 4, always starting from 0, 0, 1, 2, 3, 4. This is not this guy. 0, 1, 2, 3, 4. 4. Bit number 4 is 0. Therefore, this one. Let's do this. So now it's the second example. Copy this down. E5949010. Binary number is this. 111001. Opcode is 01. Therefore, it's a memory. So either we have this or this. So next thing, we want to check for IBIT. Either I equals to, what is this I value for this guy? 0. And this one is I value is 1. So I value is 0. Therefore, we have to have this format. We're going to look at BNL, 0 and 1. There's no byte, but is L equals to 1. Therefore, it's LDR. And then immediate, it's going to be 16. Could be minus 16. So how do you know which one? We need to look at U. It is 1. Therefore, it's a positive. So we're going to add positive 16 as an immediate offset value. And P and W is 1 and 0 is an offset. Therefore, LDR, RD, RN, and positive 16. P equals to 1, W equals to 0. It is an offset format. So we have a bracket including RN and number. Finally, RD is 9, RN is 4. So this is our instruction. And let's finish up. We have address operand, register, immediate, base, and PC relative. And we saw register only, like a add R1, R2, R3. And also immediate shift register with this guy. Logically shift to left, rotate, all of those. And register shift register, arithmetic shift to right, 8-bit of this guy, and then subtract, and then put it into R12. So those are the ones. And then immediate one, we have immediate 8 for data processing, 12 bits for the memory. We call base addressing because we want to use content of register plus offset. Okay? That offset is from 12-bit immediate. Again, that's unsigned the number. These are all unsigned the number. And then the PC relative, this is for the branch. So that's why we call it PC relative. We need to identify PC plus 8 first, and then how many lines down or up to get it into the branch target address. That's what we call the PC address. So PC plus 8 plus sign extended, this guy. And stored of the program, I mean, these are just the reading materials, you do it. And then we briefly talk about PC, program counter. So whenever we execute any given instruction, PC value is the instruction address of that instruction. It's a kind of confusing instruction address, the memory address, and so on. But it's fine. When you look at data path diagram in chapter 7, you will understand all of those.